canadiense, ha desarrollado su labor investigadora y docente en Estados Unidos y actualmente es profesor McDonnell de física en la Universidad Washington en St. Louis. Es reconocido experto en física de la gravitación, en la que se inició con su tesis doctoral bajo la dirección de Kip Thorne en Caltech. Fellow de la American Physical Society y de la American Academy of Arts and Sciences. Es autor de numerosos trabajos y libros. Tiene más de casi una veintena de artículos de puesta a punto muy importantes y sobre todo voy a mencionar dos libros que, por ejemplo, para mí, que he estado explicando gravitación y cosmología casi 30 años, han sido realmente de gran ayuda. Se ha manejado muchísimo. Sobre todo el primero, el que voy a citar, Theory and Experiment in Gravitational Physics. El segundo libro es el Was Einstein Right. Ganó un premio para los escritos científicos del American Institute of Physics en 1987 y está entre los 200 bestsellers mejores libros de 1986 del New York Times Book Review. Ha sido traducido a una multitud de idiomas, en especial al chino y al persa. Reconocimiento de su trabajo fundamental relacionado con el pulsar binario Hulse-Taylor, el 1913 más 16, que ha mencionado el anterior conferenciante, profesor Hewes, fue el profesor Clifford Will, invitado de honor de la Fundación Nobel en 1993 para las ceremonias del Premio Nobel de ese año, con el fin de pronunciar una conferencia sobre los descubrimientos de estos galardonados. Preside la International Society on General Relativity and Gravitation y el Science Advisory Committee for Gravity Probe B de la NASA. Sus trabajos sobre confrontación entre relatividad general y experiencia son consulta obligada para todos los que trabajan en las implicaciones de la teoría general de la relatividad de Albert Einstein. Profesor Clifford Will, tiene la palabra.
Einstein's general theory of relativity is one of the most remarkable creations of the human mind. This theory has changed forever the way we think about space, about time, about the universe as a whole. Some scholars even think that the influence of general relativity extends beyond science to art, philosophy, poetry, even to the course of world history. World history? My favorite example of the influence of general relativity on world history is the conservative British historian Paul Johnson. In 1983, Johnson wrote a popular history of the 20th century called Modern Times. The first sentence of Johnson's history of the 20th century is this: the modern world began on, and he gives a date. Now, if you were writing a history of the 20th century, what date would you choose to begin your history? Somebody give me some dates. What date? Anybody? Sorry? 1905, possible date, but no, that's not the date he chose. What about January 1, 1900? Or if you're obsessive compulsive, January 1, 1901? No, that's not the date. What about maybe August 1914, a very important symbolic date for the start of our modern age? That's not the date Johnson chose. Johnson's book starts, the modern world began on May 29th, 1919. What happened on that date? On that date, there was a total solar eclipse which passed over northern South America and western Africa. And during that eclipse, teams of British astronomers measured the bending of starlight as predicted by Einstein's general theory of relativity and confirmed the theory. In Johnson's book, he goes on to write that the success of relativity in science was accompanied by a rise of relativism in morality, politics, and ethics, and that this moral relativism was responsible for all the great catastrophes and genocides of the 20th century. So that would be a topic for an entirely different lecture, but I give it just to illustrate that many people feel that the influence of general relativity may extend beyond just science. Now, in 1905, as we've heard, Einstein had his miracle year, the year which we are honoring in this conference. And although he had these represent great scientific achievements, Einstein was very unknown outside the circle of European physicists at the time. Although his reputation grew steadily and he rose in the academic ranks from 1905 to 1915, he was little known outside. And even when he published the general theory of relativity in 1915, he still did not make any impact beyond the world of science. Indeed, it was very difficult for information to get out of wartime Germany in those days about his new theory. But it was really these 1919 measurements of the bending of starlight that made Einstein an international celebrity. His picture appeared on the cover of the Berliner Illustrierte Zeitung, so already he was a cover boy. And for the rest of his life, he remained an icon, the image of the scientist. And there are, of course, many famous photographs that illustrate Einstein around the world. Here with Leo Szilard drafting a letter to President Roosevelt concerning atomic weapons, riding a bicycle in Santa Barbara, with Charlie Chaplin in Hollywood, here with the Hopi Indians in Arizona, playing the violin in the Berlin Synagogue. Even music was written about Einstein. If you are a movie fan, one of the most famous and beloved songs in the movies is actually about Einstein. Well, really, the first part of the song is about Einstein. The part we all know doesn't talk about Einstein. This is a song written in 1931 by Herman Hupfield. This day and age we're living in give cause for apprehension with speed and new invention and things like fourth dimension, yet we get a trifle weary with Mr. Einstein's theory. Though we must get down to earth at times, relax, relieve the tension, and no matter what the progress or what may yet be proved, the simple facts of life are such they cannot be removed. Who can name that tune? Who can name that tune? If you love the movies, you know this song. Even in Europe, you know this. Anybody name this tune? You must remember this. A kiss is still a kiss. And of course, long after his death, he is still the symbol of science, of genius. Newsweek, within an article about genius, features Einstein. Time magazine in the US voted Einstein the person of the century. Yet ironically, although it was his general theory of relativity that brought him this worldwide fame, by the middle 1920s, as we've heard from Shelley Glashow, he turned much of his attention away from general relativity and embarked on what we now view was an ill-fated quest for a unified field theory. And around the same time, the whole subject of general relativity went into a decline. And so that by the 1950s, general relativity really was relegated to the backwaters of physics and astronomy. How could this have happened? If this was such a remarkable creation, how could this theory have gone into such a steep decline? Well, I think there were two reasons for this decline. The first reason was a sense in those early days that the general theory of relativity was too complicated for ordinary people to understand. There are many stories that illustrate this idea. My favorite has to do with Sir Arthur Stanley Eddington, one of the British astronomers who put together the expeditions to measure the bending of starlight by the sun. The measurements were made in May of 1919, but the The analysis was completed in November of 1919, and in November, Eddington made a report on his measurements to the Royal Society of London. And after his talk, as he was folding up his laptop, well, whatever they did in 1919, after his talk, one of his colleagues came up to him and with stars in his eyes said, "Oh, why, Professor Eddington, you must be one of 3 people in the world who understand the general theory of relativity." To which Eddington said, "Oh, no." The colleague said, "Oh, Eddington, don't be so modest." And Eddington said, "What modest? I can't think who the 3rd person would be." But the idea that this theory was too complicated for normal people other than a few savants to understand was an impediment to progress in the subject. It would not be a topic, for example, that would be taught in a typical physics curriculum in those days. It was simply considered too difficult. A second reason for this decline of general relativity was a prevailing feeling in those days that apart from a few very tiny observable effects, which Einstein calculated, the frequency shift of light in a gravitational field, the effect on the perihelion of Mercury, and the deflection of light, all of which I'll discuss in due course, apart from these very tiny effects, it appeared that general relativity did not have much observational contact. It really wasn't very relevant to experiment. Even Einstein's own attitude seemed to be rather blasé about experimental questions. This was illustrated in 1919 when he received a telegram from England reporting that the British teams had successfully confirmed his theory. And he very calmly showed this telegram to his student, Ilse Rosenthal Schneider. She was astonished at his very serene and calm reaction to this wonderful news. And she said to him, "Why, Professor Einstein, what would you have said if the measurements had disagreed with your theory?" And he supposedly told her, "I would have felt sorry for the dear Lord, for the theory is correct." He later wrote in 1930, "I do not believe that the chief significance of the general theory of relativity is the prediction of some tiny observable effect, but rather the consistency of its foundation and the simplicity of its formulation." But as we all know, this is not how science works. A scientific subject that is all theory with no experimental background to either change the theory, to prove or disprove it, or to move it in a new direction becomes a sterile subject. And at the same time, a scientific subject that is all experimental facts with no theory to take those facts and combine them into some coherent picture of the world also is in danger of becoming a sterile subject. The subjects in science that thrive are those where there is an interplay, an interface between theory and experiment. And I think this interface was lacking in the case of general relativity and was also partly responsible for its decline. So that by the 1950s, it was viewed as being in the backwaters of the subject. But around 1960, in the 1960s, there occurred a tremendous renaissance for general relativity. And it wasn't because of hippies or because of Vietnam, although in many ways the 1960s were a time of great ferment on many fronts. And one important front in which the 1960s were a time of great ferment was in astronomy. There was really a revolution in astronomy during the 60s that told us that general relativity would have an important role to play. 4 great events during those decades occurred that told us this. First was the discovery of quasars, about which you've heard something already. These very intense, very point-like sources of radio waves that we see today almost to the edge of the visible universe. Today we believe that the central source of the energy for these quasars is supermassive black holes weighing maybe millions to billions of times the mass of the sun. Clearly, black holes, general relativity has a very crucial role to play in black holes. The second event was the discovery of the 3-degree background radiation, the radiation that we see coming to us from a time roughly 380,000 years after the Big Bang. General relativity has obviously an important role to play in understanding the evolution and structure of the universe. Then, as we've just heard from Tony Hewish, the discovery of pulsars in 1967. these neutron stars are so dense and so compressed that one has to use general relativity to understand their structure and their behavior. And finally, just after the close of that decade, came the first detection of a black hole candidate using the first orbiting X-ray satellite. This is a black hole in orbit around a companion star, and again, black holes need general relativity in order to understand them. So these these new events in astronomy made it clear that we would have to understand whether Einstein's theory is the correct theory, because after all, you need a theory of gravity if you wish to understand these newly discovered phenomena. So that was one reason for this renaissance for general relativity. A second reason for the Renaissance, I think, was the development of a new way of thinking about Einstein's general theory of relativity, pioneered by such people as Hermann Bondi, John Wheeler, Roger Penrose, Kip Thorne, and others. A viewpoint that focused on the observable consequences of the theory, that wrote the theory in a language that made good contact with observation, rather than being bogged down on mathematical details and niceties that seemed to characterize the research of the 1920s and 1930s. This allowed one to streamline one's understanding of general relativity. It allowed one to write a whole new generation of textbooks that then permitted general relativity to be taught in universities around the world. So that these days, most graduate programs in universities teach a regular course in general relativity, and many of the larger universities even teach general relativity courses at the undergraduate level. After all, if you aren't teaching a subject to young people who are going to become the researchers of the future, again, you have a field that's in danger of becoming sterile. So this idea of teaching to the next generation was a very important factor in this renaissance of the field. And the third aspect of this renaissance for general relativity was a revolution in technology that again began around the 1960s. The technology of high precision, a technology centered around atomic clocks, lasers, masers, and also a technology coupled with the growing space program that allowed interplanetary satellites to roam through the solar system. All these things, new measuring devices, plus new satellites and new space program, permitted new experimental tests of general relativity, some of which were not even foreseen by Einstein, and at levels of precision that were unheard of in Einstein's day. And so what I want to do in this talk is to focus on these experiments that have been done to try to test Einstein's general theory of relativity. I'll begin by talking about the bending of light, the famous experiment that made Einstein such a celebrity. Then I will turn to Mercury's perihelion advance. We've heard a little bit about this already, and I'll talk about how that has turned from trouble for Newton to a triumph for Einstein. Then I'll talk about something that is actually going on as we speak here today, an experiment that has been running for the last 16 months to see whether or not space-time does the twist. You've heard me sing, but you will not see me dance. But we'll talk about what doing the twist is in space-time. And finally, I'll talk about how gravity affects time and describe why Einstein's general relativity is important in daily life. So let me begin with the deflection of light. General relativity predicts that space is not flat like the surface of this stage here, but rather is curved by the presence of matter. So matter curves space-time. In fact, general relativity says that gravity and geometry are really synonymous, that gravity really is nothing but curved space and curved time. As a consequence of this curvature of space, a light ray passing a massive body like the sun is bent, and so from the point of view of an observer, the position of the star appears to be shifted to a new location. So the principle of measuring this effect is really quite simple. You take a field of stars in the sky, say at night, take a photograph of those stars to get their exact positions, and then maybe 6 months later, after the Earth has moved around the sun and the sun is in that part of the sky, you take another photograph of the stars. And the important feature of the bending of light is the farther the light is as it passes by the sun, the less the bending. So stars that are located far from the sun are hardly, their images are hardly deflected at all, but stars closer to the sun are deflected more and more. The maximum deflection you get, for a star whose rays just graze the surface of the sun is 1.75 arc seconds. I remind you, an arc second is 1/3600th of a degree. It's the angle subtended by my finger at a distance of about 4 kilometers. Okay, so it's an extremely small angle. So all you do is take a photograph of the stars during the daytime and make this measurement. So what's wrong with this experiment? There are no stars in the daytime because the sun is up there. This, of course, is why you have to wait for a total solar eclipse. And so here, for example, is a reproduction of a plate from Eddington's actual experiment in 1919, showing the moon in front of the sun and a bit of the solar photosphere here. And now you can see stars in the vicinity of the sun. Of course, here you cannot distinguish the stars from the dirt that's on my, that's on the screen here, but I assure you there are stars between these little check marks. Unfortunately, Eddington and his colleagues ran up against a law that I discovered a few years ago. It's called Will's Law, naturally. And I'm expecting my call from Stockholm any day with my Nobel Prize for Will's Law. Will's Law states that total solar eclipses must never occur over the fine astronomical telescopes of the world. Instead, total solar eclipses must only occur over stormy oceans, steamy jungles, or swirling desert sands. That, of course, makes these experiments extraordinarily difficult. In Eddington's case, there was a huge rainstorm up until just before the totality of the eclipse. And as a result of the remaining cloud cover, he could only see a few of the stars that he had hoped to see. Even as late as 1973, when teams from Princeton University and the University of Texas went to Mauritania in Africa to do this experiment during a total solar eclipse, they had the advantage of a computer-controlled telescope and the finest Kodak emulsions for taking the photographs and a computer-generated way of analyzing the plates. They had all the finest technology. But they could control the weather no better than Eddington could, and there was a huge dust storm, and as a result of which they could see only 20% of the stars that they had hoped to see. Now, unfortunately for my Nobel Prize, my law was broken a few years ago when there was a total solar eclipse over Mauna Kea in Hawaii, which, as we know, houses many of the world's most fabulous astronomical telescopes. But I think I still may have a chance for the Nobel Prize because I'm calling that spontaneous symmetry breaking. But in the meantime, an entirely new method came along for measuring the deflection of light. And that is another one of these technological revolutions of the 1960s to which Tony Hewitt already alluded, and that's radio astronomy. With radio telescopes, and in particular with arrays of radio telescopes joined coherently together to form what's called a radio interferometer, we can today measure angles, and in particular angles between radio sources, with extraordinarily high precision, precisions reaching now better than 100 micro arc seconds. So that's 100 millionths of an arc second. So with this kind of precision, due to this advancing technology, coupled with these very quasars that I've already talked about, one could make measurements of the deflection of radio waves. Einstein's theory treats radio waves the same as ordinary optical light. The bending is exactly the same. So here's an example of one of the early kinds of experiments that was done. There are two quasars, 3C273 and 3C279. These are just catalog names for these two objects. Every fall, as the Earth moves around the sun appears to move past these quasars. So, for example, on September 28th, the sun appears here as compared with these two quasars. But since the light from the two quasars isn't passing very close to the sun, the angle between them that you measure with a radio interferometer is the standard nominal angle that you would ordinarily get. But as days go by, the sun gets closer and closer to 3C279. And so on October 8th, the rays from 3C279 are passing close to the sun. Well, here's a quiz for the audience. Which direction will the image of 3C279 move on October 8th compared to its original one? This way or this way? And you have to vote. So how many people vote that the image of 3C279 will move this way? How many vote that the image will move this way? I expect such a low turnout in America. So I expect such a low turnout in America for voters, but I presume in the Basque Country, and I understand that people have strong opinions in the Basque Country, so this is a good time to really, commit yourselves and express an opinion. So let's try again. And I should expect some hands. Nothing bad will happen if you vote wrong. So the image of 3C279 will move this way. How many vote that way? I'll allow time for the translation. Yeah. Okay, vote. How many vote that it will move this way? Better, very good. Now we're almost up to the 25% of the USA. But okay, the image moves this way. That's the correct answer. You may congratulate yourselves. And so the angle between the two quasars will appear to do what? Increase or decrease? How many vote decrease? How many vote increase? Very good. So the apparent angle will increase. The next day, October 9th, actually you'd get no data because it goes right in front of this particular quasar. Then on October 10th, which way will the image go? How many vote this way? How many vote this way? Good, we're getting the hang of it. It goes this way, and the angle will be less than normal. And then as days go by, the angle returns to its nominal value. So if you plot the angle between the two quasars as a function of time, it will increase first, one day of no data, then it will be less than normal, and then will return to the nominal value. And then you compare the shape of that curve with what general relativity predicts, and you can then test the bending of light by the sun. And in a recent analysis of the radio signals from 541 quasars using over 1.5 million observations, Steve Shapiro found that the prediction of general relativity agrees with the measurements to 2 parts in 10,000. So this is measuring angles of arc seconds and less with precisions of a few parts in 10,000. So we're operating at hundreds of micro arc second accuracy. So we really do know to very high precision that the bending of light obeys Einstein's prediction. But that's not the final chapter of the story of the bending of light. In 1979, astronomers discovered a very strange pair of quasars, shown here. These two quasars were very close to each other on the sky, which was already extremely unusual considering how far away quasars are. But furthermore, they seemed to be almost identical to each other in all their characteristics. The astronomers quickly concluded that they were seeing not two quasars, but a single quasar whose light had taken 2 different paths to reach us by going around the curved space-time of some huge cluster of galaxies that sits somewhere between us and that quasar. So in other words, the one quasar was split into multiple images by this gravitational lens, this warping of space by the cluster of galaxies. It's analogous to what you see when you're inside a bar looking out, or a pub, through the mottled glass on the window, and you see multiple images of the people outside. I would not know what that's like, of course, but some of you might know what it's like to look through the windows of a bar and see what's outside, but you can sometimes see multiple images because of the different paths taken by the light through the glass. This is exactly what's happening here, but it's not glass, it's the warped space-time due to a galaxy or a cluster. And since 1979, this field of gravitational lensing has become an important tool of the astronomers. Here are simply some beautiful examples of gravitational lenses. Here's a quasar imaged into 5 separate images by an intervening cluster of galaxies. Here's a quasar ordinarily is a very point-like object. Its point has been distorted into an arc by this same distortion of the lens. If you have a distant quasar perfectly aligned with a cluster in between us and the quasar, then the light can reach us by many different paths. This way, that way, that way. And so the one point-like quasar can appear as almost a perfect ring. So here's a ring that astronomers now call an Einstein ring in his honor. In fact, in 1912, Einstein actually worked out most of the equations that describe gravitational lenses. And here's another almost perfect Einstein ring. Here's another amazing example of a gravitational lens. This is a photograph of a huge cluster of galaxies taken by the Hubble Space Telescope. And if you take this square and blow it up, you see two very faint images here. These two images are a single galaxy that is too far away and too faint for the Hubble Space Telescope to see. But because of the gravitational lens, the warpage of space due to this cluster of galaxies, Hubble can now see this galaxy. It has been magnified. It's like adding another lens to the telescope to see further than it would ordinarily have done. So these gravitational lenses are now becoming an extremely important tool for astronomers, helping them to measure the mass distribution inside galaxies and clusters of galaxies. And this is crucial in the search for dark matter. Other kinds of lensing are being used to search for black holes, other kinds of dark matter particles, and also in the search for dark energy. So this is really Einstein's gift to astronomy that is paying big dividends and will continue to do so in the future. Let me turn now to the second of these famous successes of Einstein's general theory of relativity, Mercury's perihelion advance. In the late 17th century, you might have actually said that Newton's theory of gravity was one of the most remarkable creations of the human mind. After all, this universal theory of gravity could account for the motion of the moon, the fall of an apple on Earth, the motions of the planets, the tides of the Earth. It was one of the most extraordinarily successful theories up until then and for some time afterwards. Excuse me. But by the middle 1800s, a problem has arisen. It was pointed out by Jean-Joseph Leverrier, who at that time was the director of the Paris Observatory. Leverrier, as you all have already heard, was famous for having predicted or proposed the existence of an additional planet beyond Uranus because of the small deviations in the motion of that planet. That the new planet was subsequently discovered, the planet Neptune. But by the middle of the 1800s, astronomers knew the following about Mercury's orbit, that far from being an ellipse fixed in space with its long axis always oriented in the same direction, that's what Newtonian theory would predict for two bodies orbiting each other, far from being fixed, the orbit was precessing or rotating around the sun. So that the perihelion point, the point where the Mercury approaches most closely to the sun, was actually rotating around at a slow rate of 575 arcseconds per century. Well, Leverrier figured he could understand this precession very easily because he already knew about perturbation theory. Clearly, Mercury and the Sun are not a simple two-body system because there are other planets whose gravitational pull will perturb Mercury's orbit. So Leverrier set out to calculate the contributions of all the planets to Mercury's perihelion advance. The next planet out, of course, is Venus, and that causes a substantial effect of 278 arcseconds per century. Earth is the next planet out. It contributes 90 arcseconds to this advance. The next biggest effect comes from Jupiter. It's much further away, but it's much more massive, so it produces an effect of 154 arcseconds. Mars is a relatively light planet. It's further away. Mars, Saturn, and all the other planets that Leverrier knew at the time contribute about 10 arcseconds. And if you're adding these up very quickly in your head, you'll see the problem. The total is only 532 arcseconds, 43 arcseconds per century short of what was observed. And this was one of the great crises of 19th century mechanics. Nobody could explain this anomaly. You've already heard the proposal of a planet called Vulcan that could exist between Mercury and the Sun. If you gave it the right mass and the right orbit, you could account for the 43 arcseconds. But a planet of that mass and in that orbit would be observable. And astronomers made systematic searches for such a planet and found nothing. And every other proposal that was tried failed to account for this 43 arcseconds. Or if it did account for this, it would mess up something else in the planetary dynamics of the inner solar system. So by the time Einstein finished his general theory of relativity in 1915, November, he knew that this was an unsolved problem. No one could account for that discrepancy. So the first thing Einstein did was to realize that his laws of motion, including the law of gravity and the way bodies move in response to gravity, are slightly different than Newtonian theory. They have Newtonian theory as a first approximation, but there are small correction terms. Some of us call them post-Newtonian correction terms, additional correction terms that will affect Mercury's orbit. And so Einstein sat down to calculate the contribution of those additional terms. And lo and behold, he got 43 arcseconds per century. He later wrote to a friend that when he discovered this, he had palpitations of the heart, and he could not sleep for weeks because of the joyous excitement of this great discovery. If you can imagine having resolved a long-standing problem with such a simple calculation, one can only sort of imagine what he must have felt like. But the story actually doesn't end there. We now know with much better accuracy than Einstein knew in his day all the numbers that go into this chart. We know the actual motion of Mercury with much better accuracy than before, mainly through the technique of radar ranging, bouncing radar signals off Mercury's surface and also ranging to some of the planetary spacecraft that have orbited Mercury. So again, this is modern technology brought to bear on this problem. In addition, because of planetary spacecraft that have gone by other planets, we now know the orbits and masses of many of these planets to much higher accuracy than before, so allowing us to calculate these contributions with extremely high accuracy. So the upshot is that today, the modern value of the discrepancy that has to be explained is 42.98 arcseconds per century plus or minus 0.04 arcseconds per century. The actual prediction of general relativity is exactly on. So to a part in 1,000, general relativity agrees with the observations of Mercury's perihelion. Let me turn now to whether space-time does the twist. So I've already told you that a massive body warps space-time, warps space and causes things like the bending of light. But in addition, when a body is rotating, it has a tendency to drag space-time around with it, much as if you took a stick and put it into a vat of molasses and turned the stick slowly, the molasses would start to swirl around the stick, being dragged by the friction of the stick. And so that slow dragging of space-time is a prediction of general relativity around any rotating body such as the Earth. And for the past 16 months, since its launch in April of 2004, a NASA experiment called Gravity Probe B has been in the process of trying to measure this effect. What they have done is to put into orbit around the Earth an array of gyroscopes, 4 gyroscopes, so little spinning balls, and the idea is to measure any small change in the spin of those gyroscopes relative to some distant object, in this case, a star in our galaxy called IM Pegasus. The spacecraft has a telescope that is always pointing at this distant star, and so it measures the precession or change of the spins of the gyroscopes relative to the telescope axis. The effect that they want to measure is extremely small. It's 42 milliarcseconds, 42 thousandths of an arcsecond per year. That's this dragging effect, sometimes called frame dragging. There's actually an additional effect on gyroscopes called the geodetic effect, and that's simply a result of the gyroscopes moving through the warped space-time around the Earth. But this effect, the smaller one, this is quite substantial, 6.6 arcseconds per year, but the smaller one is the one that one really wants to measure. It's never been measured precisely before, and this is due to the rotation of the Earth dragging space around with it. This is an extremely important effect because many astrophysicists believe that this frame dragging effect in a much more exotic context is responsible possibly for the way quasars emit their power. A rotating supermassive black hole has such strong frame dragging effects that those effects may tell us something about how these quasars emit their energy. So this frame dragging may have important astrophysical consequences, therefore we'd like to really measure it to see if it is there. The goal of this experiment is an accuracy of about 0.4 milliarcseconds per year, so they hope to measure this to about 1%. It's a 16-month mission. In fact, it is probably in its last days right now. Here's a sort of a picture of the spacecraft. Here inside a quartz block are the 4 gyroscopes. I'll show you a picture in a moment. And there's a telescope here, and the telescope points toward the distant star. And this is a large container filled with liquid helium at 1.8 Kelvin, 1.8 degrees above absolute zero. This experiment exploits another sort of other bits of modern technology, in this case superconductivity and superfluidity, to allow them to make very precise measurement of this effect. So the liquid helium is crucial to the operation of the experiment. There's a picture of one of the gyroscopes. It's a fused quartz sphere with a thin coating of niobium around the sphere, and that's a thumb, and those are fingers. So you see how big each of these spheres is, about that big. Each sphere is spinning at about 100 cycles per second inside the spacecraft. And in order to reduce anomalous sources of changing direction of the gyroscopes, anomalous torques, these gyroscopes have to be perfectly spherical and perfectly homogeneous. And they have been machined that way to parts in 10 million. And here's a test of how spherical these gyroscopes, or one of these gyroscopes is. Using lasers, one can measure the height of the highest mountain on this gyro and the depth of the deepest valley on this gyro. And the scale here is measured in micro inches. So if you were to take this gyroscope and scale it up to the size of the Earth, the difference in height between the tallest mountain on that Earth-sized gyro and the deepest valley would be my height. That's how spherical these gyroscopes are. That reduces any other sources of movement of the spins so that you can really look only at the relativistic motion. Because it's in a spacecraft filled with liquid helium, the helium boils off continuously, and the mission was scheduled to last for 16 months, and it has lasted exactly 16 months, and I've just learned yesterday that there's only a very thin film of helium left on the outer edge of the spacecraft. When that boils off, the mission will end as planned, and they will stop taking data. It will be about a year of data analysis before we actually know, in this case, whether Einstein was right about this frame dragging effect. But maybe a year from now, we perhaps will have a report one way or the other. Finally, let me talk about the effect of gravity on time. So I've talked about how, according to general relativity, massive bodies cause a warpage of space, a curvature of space. But mass also causes a curvature of time. It makes time evolve differently depending on where you are relative to a massive object. So in particular, an object far from the Earth, a clock on such an object ticks a little more rapidly than a clock on the surface of the Earth. Now this frequency shift or time shift due to gravity has been measured and tested many times before. The most precise experiment to date was done in 1976 in a mission that was actually called Gravity Probe A. So that's where the B comes from in Gravity Probe B. This was an earlier experiment by NASA, in which a hydrogen maser clock, this was the most precise and stable kind of atomic clock known in the 1970s, one of those clocks was put on a rocket and launched to an altitude of 10,000 kilometers, and the rate of that clock was compared by sending telemetry signals back and forth with an identical hydrogen maser clock on the ground. In this case, of course, there are two effects you have to include. One, of course, is general relativity. Because of the curvature of time, the clock on the satellite ticks more rapidly than the clock on the ground. But in addition, this rocket is moving at high speed relative to the clock on the ground, so there's the special relativistic slowing down the time dilation effect that Tony Hewish talked about a little earlier. So it's a combination of the two effects that was measured. And in this 1976 experiment, the measurements agreed with Einstein's prediction to 2 parts in 10,000. So once again, a high precision test of Einstein's predictions. So what does this have to do with daily life? I told you that general relativity may be important in daily life, and as already mentioned, it has to do with the global positioning system. Let me explain briefly how this system works. It's a system of 24 satellites that orbit the Earth. They're at a distance of 4 times the radius of the Earth. That's their orbital radii. Each satellite carries on board an atomic clock. In most of the cases, they are cesium atomic clocks if you have rubidium standards. Each satellite broadcasts to Earth a coded signal that contains the following information: the time when that signal was emitted, and the location of the spacecraft at that time. And the orbits of the spacecraft are known very precisely and are constantly improved and updated, so we have very precise knowledge of their orbits. So now if you're sitting here on Earth and have an atomic clock with you, you can determine the time when that signal arrives. So if you know the time that it was sent, and you know the time that it arrives, what can you learn? Anybody? You're smiling. What can you learn? If you know the time it arrives and the time it was sent, and you know the speed of light, you can measure what? The distance. So you know how far you are from this satellite. That tells you you must sit on this arc of a circle. Now, if you can get this data from a second satellite, then you learn that you must sit on this arc. And since you must sit on both arcs, you therefore sit at this intersection point. And then if you can get this information from a third satellite, you can determine your location in altitude, latitude, and longitude. Now, let me see a show of hands. How many people carry an atomic clock with them on a routine basis? I didn't think so. But GPS has been designed so that at any moment of time, you can typically see 4 satellites. So in fact, you can then use the 4th satellite as a way to go back and determine what that time would have been if you had an atomic clock by you. In fact, from a relativistic point of view, this is really a space-time problem. You can determine your location in space-time, 3 spatial locations, latitude, longitude, and altitude, and your local time. You have 4 unknowns, you get data from 4 satellites, that's all you need to get your location and your local time. Of course, a little microprocessor in your GPS receiver does all the work for you. But with just the modestly priced GPS receiver, you can determine absolute location on Earth with a precision of 15 meters and absolute time to 50 nanoseconds, or 50 billionths of a second. So this obviously has important navigational applications. We know if you own some of the high-end cars, you have GPS receivers in your car telling you where to go. GPS is being used more and more in aircraft guidance. Obviously, it's used in missile guidance, has many military applications, and the ability to transfer time with 50 nanosecond accuracy has obvious military and scientific applications. But it's crucial that all the times and clocks in the system are accurate and synchronized to this kind of accuracy if you're going to get to 50 nanosecond accuracy if the system is to work. So what does relativity have to do with this? Well, as I've told you, clocks on the satellites tick a bit more rapidly than clocks on the ground because of the curvature of time. Also because of their large motion, there's a backwards effect, slowing down of time because of special relativity. But one tends to think of these as being tiny effects because most of my talk has talked about very tiny effects. But here's a case where technology has caught up with Einstein, and relative to the technology of GPS, the effects are enormous. GPS clocks on the satellites tick more rapidly than clocks on the ground by 39,000 nanoseconds per day. Compare that with the requirement of accuracy at 50 nanoseconds at all times. In other words, if you did not take relativity into account and you turned on the GPS system now, then within a minute and a half it would fail because the different rates of these clocks would cause an error bigger than 50 nanoseconds. Relativity must be taken into account and is routinely taken into account in the GPS system. General relativists, of course, as you might guess, don't have much to talk about when it comes to practical applications. So here's one example that we like to talk about all the time. We love GPS, we relativists, because it's one practical example of general relativity that we can point to. But in fact, there's a bit more to this story that actually affects me a bit personally. Back in the middle 1980s, when GPS was in its early phase, only about 6 satellites were in orbit at that time. The Air Force, which was then running the GPS program, began to be worried about whether or not they were doing these relativistic corrections properly. And so they asked me to put together a small committee of experts to study their procedures and to report to them as to whether or not they were doing relativity properly. In the course of our study, we concluded actually that they were doing all the corrections right, they had all the right equations, they were doing everything perfectly. But at the end of our study, I had to make a final report on our results to this Air Force general, who was then in charge of the Air Force Systems Command. So I had to explain to this general a little bit about general relativity in order to justify the study. So I prepared a lecture that was extremely simple. And I had the most colorful view graphs that I could have. And I jumped up and down and I waved my arms a lot. Within 15 seconds, his eyes closed. But luckily, his aide back here, she was taking furious notes while I was speaking, so I presume that she told him afterwards what I had talked about. But for a general relativist to be teaching general relativity to an Air Force general, because it's important for the national security of the United States and many other countries, for me this was seventh heaven. And as you may have spotted, there I am with much longer hair and much younger than I am now. So in this talk, I've tried to give you some feeling for the kinds of experiments that have been done to try to test Einstein's general theory of relativity. I asked the question, was Einstein right? And I won't answer it for you. I'll let you draw your own conclusions, because that's, after all, what the scientific method is. You evaluate the data, compare it with the predictions, and you draw your own conclusions. But to me, the most remarkable aspect of this story is that Einstein developed the general theory of relativity not driven by observational criteria or by a desire to explain some experiment. He was driven almost purely by aesthetic criteria of elegance and simplicity and coherence and internal consistency. To me, the most amazing thing is that here we are 100 years after special relativity and 90 years after general relativity. The theory still seems to be right after all. Thank you very much.